Hello students, welcome back to Engineering Mechanics Dynamics. This is Dr. Hawk. At lecture 3 today, we're going to study curvilinear motion. So let's begin. So today's learning objective is describe the concept of position, displacement, velocity, and acceleration. We have learned this concept in lecture 1, but today we're gonna learn the same concept for curvilinear motion. In the first lecture we were studying rectilinear motion. Today we're going to study curvilinear motion, and we'll see if it is any different than rectilinear motion, and we'll derive any formula needed for curvilinear motion. In addition, we're going to study particle motion of a projectile. So how a motion of a particle would be if it's assumed as a projectile. So let's move on. So what is curvilinear motion? Generally, when a particle is moving along a curved path, it is so we can say it is experiencing curvilinear motion. So for example, if we have a particle that is moving along this path, and this is my particle, then we can call this particle is having a curvilinear motion because it's following a curved path. So you can see the particle in every instant, every position is changing its direction and position. So for curvilinear motion, we always have to represent it in a vector form. For example, if we have an origin here, and we say it's in R position, it's a vector. So we have to represent that the particle current position is represented by this R vector that has a magnitude and direction. So in curvilinear motion, we have to present the position, displacement, velocity, or acceleration in vector form. Now let's see how it would be if we want to define position for curvilinear motion. So the position vector of this particle would be represented by R vector, which is actually a function of time, because in every time it's changing. So R would be a function of time. So how about displacement? So let us assume that the particle path is like that, and then after a small time amount, the new position of the particle here is R1. So now, in vector form, we can write the new position R1 as a change of R vector plus we have to draw another vector here. We are assuming this two position of this particle here and here is so close that we can assume that the curved path is linear, and this is represented by delta vector R. So we can say the displacement, the position vector of the position vector of the particle at this position can be represented by R1 equals to the vector R and then the delta R. From here we can get the change of position, which is displacement, is r1 minus r. So this is the displacement. So once we have defined the position, and we're gonna see how this vector are present, has different coordinates, but for now we have seen position and displacement in vector form. Now we're gonna study velocity. So for the velocity, we in lecture 1 we saw that there's two ways we can find velocity, which is average velocity and instantaneous velocity. So for the average velocity, we know it is the change of displacement. Again, it is in vector form, so we'll have both as a vector change over time. So time doesn't have a direction, so this remains scalar, but the r will be in vector form. So this is the average velocity, and we can find the instantaneous velocity again by taking derivative of the vector r and with respect to time. So we know the vector r can have components, directional components. For example, for a rectangular coordinate system, it may have x, y, and z components. So we have to do derivative with respect to time of x, z, y, and z components. We're gonna see that in a little bit. So let's move on to next slide. Speed. So how about speed? Does speed defined differently when we're talking about curvilinear motion? Well, not so, because the speed is the magnitude of the velocity. So speed, we can get it as the same way we had defined before, derivative of displacement with respect to time. And we're gonna see more when we do solve our problems. So after velocity, we know we have to define acceleration, and again, acceleration has two forms: average acceleration and instantaneous acceleration. So average acceleration would be the change in velocity with respect to change in time. So if we have particle that is moving with respect to origin O, it has previous velocity, which is tangent. Velocity will be the tangent of the curve. So this velocity v, which is a tangent to the path of the particle, and after time delta t, the new velocity at this position, for example, it is v1. Both of them are vector, and this v1 and v are tangent to the particle path. So the change will be delta v. So we can say the average velocity is delta v over delta t. The instantaneous acceleration, again, it's a vector. We can get it by taking derivative of vector form of velocity with respect to time. Or we know that this one, the vector velocity is defined by r over dt. So if we plot that, we can also define acceleration as second derivative of vector r with respect to time. So we see that these are not so different than the first lecture we have studied, the concept of position velocity, displacement, and acceleration, but all we have to consider is the vector term, and it will make the work a little bit complex, but not so, and we'll solve problem, and we'll see how to address um, this vector form, so that we can do the derivative. So next we're gonna study direction components. So before that, one thing, so we told you that the velocity is tangent to the path. So what would be the direction of acceleration? Acceleration is not tangent to the path of the particle. Here, say acceleration is not tangent of the path of the particle. It is tangent to the vectorial visual representation of the movement of the body of the particle. So we call it hodograph. So acceleration would be tangent to the vector form of velocity, which is another term is hodograph. Okay, so let's move on. Direction components. So we know if it's in vector form, it can have for example, in rectangular components, we will have x, y, and z components. So often curvilinear motion follows a three-dimensional path. So curvilinear motion are represented often in three-dimensional path, and the particle motion is described easily in directional components. So we know the most common one is a rectangular component when you have x, y, and z coordinates, and then you can have a tangential and normal component. So if your particle is moving, you can have a tangent component of that particle position, and normal, so which is 90 degree to the tangential component. So you can have a tangential and normal components, and there's a cylindrical components. We're going to study all of those one by one, but we'll start with the rectangular components today. So rectangular components, we know it's x, y, and z coordinates. We already know that, so let me draw one. If this is my origin, and we assume it x, y, and z. We also know that this x, y, and z has a unit vector that is represented, directional unit vector is for x, it is I, for y it is j, and for z it is k unit vector. So assume that we have a particle that is in the space right here. So if we would like to define the position of that particle, we can say that it has three components, x, y, and z. So this height from the xz plane would be the y, and if we take x intercept, we'll get the x position x, and if we take this component, we'll get the position z, the coordinate z. So from origin to that particle, we'll get the coordinate xyz from the xyz rectangular coordinate system. So how in vector form we can define the position vector r of that particle. So we just saw the x component, y component, and z component. So x, y, z, these are presented in summation form with the direction unit vector. Just what I said. So this x value would say this is the position in x direction, which is represented by the I, and this value y is the height from the origin, which is represented by j, meaning in y direction, and z value would say it's in k direction, so on z axis. So these are the unit vector I, j, k on x, y, z axis, but the position vector r, it itself has a direction. And how do we get the unit vector on that direction? To get that, it's represented by ur, and since it's a unit vector, so if we divide the vector with the magnitude of the position vector, we'll get the unit vector. So how do we get the magnitude of the position? So it's easy. If we take the magnitude of x, y, and z squared divided by square root, we will get the magnitude r. So magnitude of the position vector r. So once we have the position vector, now we can find the velocity, which would be taking the derivative of position vector r. And you know, r has three components here. R has three components. So how, if we simplify and expand that form, we can get this three term. So let me explain you a little more. If we take all three term for derivative, we'll get d over xi dt, and same for d over x yj, so plus d over xj, d over yj over dt, plus d over zk dt. So now let's solve one term. We see if we expand that, we'll get dx dt I plus, so we're just solving, expanding this term. If we do this, we'll get dx dt multiplied by I plus x di over dt. So now I is a vector, and unit vector, this is constant. So if we take a derivative of constant, it becomes 0. So we left with, so this one becomes 0, so this whole term becomes 0. So we are left with this term only, and you see this is identical to this part here. So same thing for this term and this term, we'll get this term and z term. So this is how we get the velocity. We also we can define dx dt as a simplified form is a velocity component x. So it can be written simplified form like so. So this is the derivative of the position x with respect to time in x direction, so it's vx, and similarly vy and vz, and then the unit directional vectors. So how about the magnitude? Magnitude is the same as we did it for position vector r. So velocity is square root of v square, velocity y component square and z component square, and square root all over it. So we'll get the magnitude of velocity v. So let's move to the next slide. So acceleration, again, we can follow the same way that we just talked about velocity. So acceleration would be time derivative of velocity vector. So again, the vector has x, y, and z component in rectangular components. So x part, y components of the velocity, and z component, and it will have the y, j, k components. I know the vx also represent, we know that it can be represented as rx time. So x component of the position, so dx over dt. So if we plug that here, we get a second derivative with respect to position x, and it will be y, and this one would be j. So second derivative with respect to y and j, z. So if we consider ax equals to second derivative of x dt square, or ay equals to second derivative of y dt square, and same for z, so we can find the simpler form for the vector, acceleration vector a, and then we can get the magnitude as the same way we did it for position and velocity, like so. So now we have studied the position, velocity, and acceleration for a rectangular coordination system. We found the components. So now we'll study, so next we will study tangential components and then cylindrical components. But before that, we need to study another concept that we're going to use in problem solving, so which is motion of projectile. So projectile motion. So when we say that we have a projectile, we can say, in if it's x and y direction, if my particle was here, which could be in any height y, in an x is origin O, so any position in x direction, if if the particle is thrown and is following a curvilinear path, it's the final position of that particle. So we can assume that the particle was thrown in this direction with the initial velocity u bar, meaning it's a vector. And it can after a particular time, it has a new position, which we can define by y1, and new position x1. So we can see that this initial velocity u can have a x component, which I can say ux, and a y component, which is uy, and at this position, it has the velocity v, which is in vector form. It also have a x component vx and a y component vy. So when we assume motion of a projectile, we assume that it's a particle form. It's thrown near Earth's surface, meaning it will have a gravitational force acting on the body. But if we assume it's in some other places, for example Moon or Mars, then only thing will change is the gravity. For Earth, we know it is z, which is 9.81 meter per second square. It will be changed if we assume it's the particle was thrown on Moon, on Mars, or somewhere else. So, but now for now we're assuming it's near Earth, and we throw the particle. It moves along a curved path. Though it's thrown in air, we neglect the air resistance, so we will not consider air resistance during our problem solving. And only force, only acceleration. So only acceleration acting on the body is the gravitational acceleration, which is z 9.81 meter per second square. Nothing else is acting on the particles. So once we made this assumption, now we can define some formula that was similar that we have developed in lecture 1. Remember, in lecture 1 we have defined some formula, derived some formula for velocity and position. So we're gonna use those formula and then redefine them for projectile case. So in previous slide we saw that the particle was thrown in u initial vector that may have an u that will have an ux and uy component. So for horizontal motion we are considering the horizontal part only, and we will not consider the vertical scenario. So in horizontal, and then we know that the acceleration, gravitational acceleration, works in y direction. So the acceleration for horizontal motion is 0. So we had derived the formula in lecture 1 is that v velocity is equals to initial velocity and acceleration multiplied by time. For horizontal motion, this will be simplified to final velocity equals to initial velocity, because acceleration is 0. So in x direction, so this is not in y direction only. Y direction is only in x direction. Velocity component vx is equals to vy. So no change in the x component throughout the travel of the projectile. Now we have seen that we also had derived the formula delta s equals to initial velocity multiplied by time plus half acceleration time square. So if we apply this formula to horizontal motion, we'll see that acceleration is 0 again. So delta s change in position in x direction. So notice one y direction, only in x direction. Delta x is again only initial velocity component ux multiplied by time. So the displacement in x direction will be initial velocity multiplied by the time it traveled. The final formula we had v square equals to initial velocity square plus twice acceleration and delta displacement. If we apply that for horizontal motion, we'll get final velocity. Again, acceleration is 0, so initial velocity square, that gives us vx equals to ux, which is the one we already proved up here. So these are the three, well, actually two. These two are the equation for horizontal motion of that projectile. So now, what about the vertical motion? We can use the same formula that we used here to derive the vertical motion scenario. So again, we had the v, final velocity equals initial velocity, acceleration multiplied by time. If we consider the y component of the velocity, now we see that we have the y component of the initial velocity, and acceleration is not zero. So now acceleration is equals to gravitational acceleration z. So we'll say negative zt. So why it's negative? Because z is acting downward, and the velocity, the u, was thrown upward. So it was moving upward. So if we assume that as a positive direction, now my gravitational pull is downward, so we assume this is negative, because the particle was thrown upward, so the u is upward, the y component is upward, and then gravitational pull is c downward, so we assume it's negative. So this is one. Now for the second one, delta s, we had ut plus half at squared. If we plot the scenario of vertical motion, so we'll get delta s in y direction. So how much it will go up is again y directional of initial velocity multiplied by time, and negative half gt squared. So acceleration is equals to z now, and then it's negative because it's acting in the opposite direction of the particle was thrown. And final equation is v square that we had in the initial velocity square plus twice a delta s. If we apply that formula, we can get, so this is the second one. Okay, we can get vy square equals to u y component of the initial velocity whole square plus twice negative twice g delta s in y direction. So these are the formula for vertical motion. So so we have seen that if it's a particle was thrown and it's acting as a projectile, it will have x and y component. So for the horizontal part of the motion of that particle, we will use these equations here, and for the vertical part of the motion of that particle, we'll use these three equations. Okay, so summary, we have studied position vector, which has a for rectangular coordinate system. R can be represented by x, y, and z in I, j, k unit vector. The magnitude we can find using this formula. The velocity and acceleration follows the same format. If we take derivative of the position vector, we'll get velocity, and if we take derivative of velocity or double derivative of the position, we'll get the acceleration. For horizontal motion, we see that our simplified form of the formula that we derived in lecture 1 is that for horizontal motion, the final velocity is always same as the initial velocity, and then the displacement in x direction is simple, it's just the initial velocity multiplied by the time. For vertical motion, we'll have a little bit complex, and or a little bit is almost same as that we derived in lecture 1. So y component velocity is equals to the initial velocity minus gt, which is the gravitational acceleration, 9.81 meter per second square, and then the y direction displacement would be initial velocity, y component of initial velocity multiplied by time minus half zt square. So this, just remember, this is negative because the particle was thrown upward and gravity is z downward. That's why it's minus. If the particle was thrown downward, so if my u was downward, then my components x and y would be downward, so this minus will then become positive. Just remember that, and we'll solve problem and we'll see that And the final another form of velocity equation is v square y component with the y component of initial velocity minus um, minus minus 2z delta s in y direction. This would be y. Okay. So in that was it for today. In next lecture, we're gonna study. Next video, we'll solve some curvilinear kinematics problem. We have so far solved rectilinear problem. So we'll also solve some curvilinear problem, and we'll also solve some problem on projectile motion or motion of projectile. Thank you so much.